So next chapter is optics of ametropia. In contrast to ametropia, the ametropic eye fails to bring parallel light to a focus on the retina. So the second principal focus of the eye does not fall on the retina. So the ametropia consists of myopia, hypermetropia, and astigmatism. So first of all, the myopia. In myopia, the second principal focus that lies in front of the retina. So the myopic eye fails to bring parallel light to a focus on the retina. So the second principal focus lies in front of the retina. The myopia may be of two types: axial and refractive or index. In axial myopia, the light rays falls in front of the retina due to increase in the axial length. So this is called axial myopia, in which the eye may be abnormally long and there may be a posterior stapyloma in high myopia. Alternatively, the eye may be of normal length but the diopter power may be increased. This is known as refractive or index myopia. The eye is of normal length but the diopter power is increased. Example of refractive myopia or index myopia is keratoconus, where the corneal refractive power is increased. So the problem is in the cornea. And in nucleosclerosis, where the refractive power of the lens increases as the nucleus becomes more dense. Next is hypermetropia, in which the eye fails to bring parallel light to a focus on the retina, and the second principal focus lies behind the retina. It is also of several types like axial. In axial, the eye is short relative to its focal power. In refractive, the eye is not short but the refractive power of the eye is inadequate, as in apecia. Hypermetropic patient can overcome some or all of their hypermetropia by using accommodation for distance vision. They bring this focal length on the retina by using accommodation. They then have to exercise extra accommodation for near vision. So for distance vision they correct this, but for near vision then they have to use more accommodation. Now, because the amplitude of accommodation declines with age, the hypermetropic patient requires reading glasses at a younger age than ametropic patients. There are other types of hypermetropia also. Total hypermetropia is the amount of hypermetropia with all accommodation suspended by using of cycloplegic drugs. For example, cycloplegic refraction, which we do for children. So to know about all the total hypermetropia. So total hypermetropia further divided into manifest hypermetropia and latent hypermetropia. Manifest hypermetropia, it is the strongest convex lens correction accepted for clear distance vision. And latent, it is the remainder of the hypermetropia which is masked by ciliary tone and involuntary accommodation. Latent hypermetropia in simple words is the difference between non-cycloplegic refraction and cycloplegic refraction. So if you do non-cycloplegic refraction and give a strongest convex lens and then you do cycloplegic refraction, the difference is the latent hypermetropia. Manifest is further divided into facultative and absolute. Facultative hypermetropia, which can be overcome by accommodation. Absolute hypermetropia, so it is the hypermetropia which cannot be overcome by accommodation. It is the weakest convex lens correction accepted for clear distance vision. The latent hypermetropia, so it is for latent hypermetropia, cycloplegic refraction is necessary because this may account for several diopters, especially in children. So cycloplegic refraction is necessary to find the full magnitude of refractive error. So to find the full magnitude of latent hypermetropia, cycloplegic refraction is necessary. While the manifest hypermetropia, there is no need of cycloplegic refraction, you just give the strong convex lens. So it can be found by only convex lens, while latent by cycloplegic refraction. So again, total divided into manifest and latent. Manifest by facultative and absolute. Manifest can be found by convex lens while lightened by cycloplegic refraction. Now astigmatism. So in astigmatism, the refractive power varies in different meridians. Suppose this is one meridian and this is another meridian. So they both the meridian have different power. So the image is formed as a strum conide. One meridian focused light here, while another meridian focused light here. So this forms strum conide. It is divided into regular and irregular astigmatism. In regular astigmatism, both these meridians are at 90 degrees to each other, while in irregular astigmatism, they are not at 90 degrees to each other. It cannot be corrected by spectacles, the irregular astigmatism. So no astigmatism, regular astigmatism and irregular astigmatism. The regular astigmatism is further divided into with the rule astigmatism, oblique astigmatism and against the rule astigmatism. In with the rule astigmatism, it is a type of astigmatism where the vertical meridian are the cornea. This is a vertical meridian. It is steeper than the horizontal meridian. So astigmatism occurs when the cornea curvature varies in different meridians. So the light rays focus unevenly. So in this with the rule astigmatism, the steepest meridian is within 30 degrees of 90 degrees. 30 degrees on this side and 30 degrees on this side. Or we can say it is between 60 and 120 degree. So to correct this with the rule astigmatism, a concave cylinder is placed at 180 degree plus minus 20 degree, or a convex cylinder is placed at 90 degree. Concave cylinder is placed at 180 degree or convex vertically. And against the rule astigmatism, the horizontal meridian is steeper. So or we can say the horizontal meridian between the 30 degree or 170 degree. So the steepest meridian is horizontal or within the 30 degrees of the 180. 30 degrees of the 180, between 30 and 150. The third type is oblique astigmatism, which occurs when the steepest curve is between 120 and 150 or in 30 and 60 degree. 120 and 150 are between 30 and 60 degree. Astigmatism is classified according to the image position relative to the retina and to simple myopic, simple hyperopic, compound myopic, compound hyperopic or mixed astigmatism. In simple myopic and simple hyperopic, you can see in simple myopic, a focal line is on the retina and the other focal line lies in front or behind the retina. So this is simple myopic, one focal line on the retina, one in front of the retina. In simple myopic, hyperopic, one focal line on the retina and one behind the retina. Compound myopic, compound hyperopic astigmatism, both focal lines are in front or both are behind. Both focal line in front, both are behind. Third is mixed astigmatism, in which a focal line lies in front of the retina and one focal line lies behind the retina. And isometropia, when the refraction of the two eyes are different. Small degrees of anisometropia are commonplace. Large degrees are a significant cause of amblyopia. So more than one diopter disparity in the hypermetropic patient, it is enough to cause amblyopia of the more hypermetropic eye. Why? Because accommodation is a binocular function. So the individual eyes cannot accommodate by different amount. So the more hypermetropic eye will remain out of focus and it will become amblyopic. While the myopic patient with anisometropia is less likely to develop amblyopia, because both eyes have clear near vision. However, when one eye is highly myopic, it is usually becomes amblyopic. Now older patient with nucleosclerosis, so it will result in index myopia and it will affect one eye more than the other. So then these patients may not tolerate the full spectacle correction of the more myopic eye because they are not accustomed to coping with anisometropia. While the myopic patients who have been anisometropic all their lives, they tolerate high degree of anisometropia and they achieve binocular vision with more than 2 diopter difference between the two eyes. Next is pinhole or stenopic aperture test. So this is a pinhole and optimal size is 1.2 millimeter. This pinhole theoretically allows only one ray from each point of an object to pass through to the screen. Thus a clear image is formed regardless of the position of the screen. Likewise, the use of the ideal pinhole leads to the formation of a clear retinal image irrespective of the refractive state of the eye. But in practice, the pinhole available clinically allows a narrow pencil applied to pass through them rather than a single ray. So, in ametropic eye, there is no focused image and the visual acuity is reduced. So this pinhole test is a useful method of determining whether the reduced visual acuity is due to refractive error rather than ocular pathology or neurological disease. If the visual acuity is reduced by refractive error, this pinhole acuity will be significantly better than the unaided acuity. But if the reduced acuity is due to ocular pathology, there is characteristically no improvement in visual acuity with the pinhole test. If there is macular disease, then pinhole acuity may be even worse than the unaided acuity. In low degrees of refractive error, the pinhole effect is sufficient to improve the clarity of the retinal image to such an extent that a good visual acuity results. However, in high degrees of ametropia, although pinhole helps, the retinal image is still too diffuse to achieve the improvement that is found in the case of low refractive errors. Thus, errors outside the range of +4 and -4 are not corrected to 6x6 with pinhole. Next topic is stenopic slit. This is the stenopic slit and it can be used to determine the refraction or to determine the principal axis in astigmatism. This is the slit aperture. It acts as an elongated pinhole. It allows light in the axis of the slit to enter the eye and the other axis is blocked. Hence, when the slit lies in one principal axis, suppose in this principal axis of the astigmatic eye, the second line of focus is eliminated. This will be eliminated and the blur of strum conide reduced, thus allowing a clear image. So only one meridian light is passed, so a clear image is formed. So when the slit lie in one principal axis, the second line is eliminated and the blur conide strum reduced and this clear image is formed. Now how refraction is done in principal axis are determined. How? So during the refraction of a patient with astigmatism, the slit is first rotated to a position in which the clearest vision is obtained. So then the spherical lenses are added to give further improvement in acuity. The slit is then rotated through 90 degree and the spherical lens power adjusted to give best subjective acuity. The cylindrical correction required by the eye equals the algebraic difference between the two spherical correction used and its axis is that of the original direction of the slit. In cases of corneal scarring, the stenopic slit may be used to determine the meridian along which the cornea is least deformed. In those cases where an optical iridectomy is indicated, this should be performed in this meridian. So, optical correction of ametropia. How to correct myopia, how to correct hypermetropia. Before this, we should know about the far point. The far point FV of an eye, it is the position of an object such that its image falls on the retina of the relaxed eye in the absence of accommodation. The distance of the power point from the principal plane. This distance is denoted by R. Which according to sign convention carries a negative sign. So here you can see negative sign in front of the principal plane and a positive sign behind the principal plane. So this distance is negative in front of the principal plane and positive behind the principal plane. So now optical correction of these ametropia. The purpose of the correcting lens in ametropia is to deviate this parallel light, incident light, so that it appears to come from the far. So that it appears to come from the far point in myopia, or in hypermetropia. The purpose of corrected lens is to deviate parallel incident light so that it appears to be converging towards the virtual far point in hypermetropia. The light will then be brought to focus by the eye on the retina. Thus the far point of the eye must coincide with the focal point of the lens. The focal length, this is f, of the correcting lens is approximately equal to the distance r. This distance r of the far point from the principal plane when the correcting lens is close to the principal plane. Thus the power of the lens will be inversely proportional to this focal length, or inversely proportional to this distance. So this capital F is the power of the lens in diopter, while the small f is the focal length of the lens in meter, or is the distance of the far point from the principal plane in meters. R and F are almost equal. So the reciprocal of the far point distance R in meter is symbolized also by capital R expressed in diopters. So this R is known as static refraction or the ametropic error. Now effective power of lens. So suppose this is a correcting lens. It is moved either towards or away from the eye. So in this case away from the eye. So this is a convex lens and it is brought away from the eye. So the vergence of the lens, the vergence at the principal plane of the eye, it will changes. In the focus of the lens, in the far point of the eye, no longer coincide. So this is the far point. So in this case it coincide. Well, in this case the far point in the focus of the lens, they do not coincide. So the image is changed. The image is also moved forward. So this is a hypermetropic eye which is being corrected by convex concave lens. Sorry, this is convex lens, and the purpose of this correcting convex lens is to bring the image forward on the retina. So when the correcting lens is moved away from the eye, the image is brought still forward. So from this diagram you can see that the effectivity of the lens is said to be increased. Therefore, in this position, a weaker convex lens throws the image onto the retina and corrects hypermetropia. Now, this is a myopic patient, which is corrected by the concave lens minus lens. The purpose of this concave lens is to take the image back on the retina. So when the correcting lens is moved further away from the eye, the image moves forward again. So the effectivity of the lens is said to be reduced. So in this position, a stronger concave lens is needed to throw the image on the retina. So in practice, patients with strong convex lenses, especially those who are epic, sometimes pull their glasses down their nose in order to read. The enhanced effectivity thus produced is sufficient to provide the reading correction. Also, myopes dislike their glasses slipping down on their nose, as they tend to do if heavy glass lenses are used, as this makes the correction less effective. So to correct specific degree of ametropia, a power of the correcting lens must be adjusted to take into account its position in front of the eye. Now, to correct a specific degree of ametropia, the power of the correcting lens must be adjusted to take into account the position in front of the eye. So a general formula exists for this purpose and applied both to concave and convex lenses. Suppose a length of a focal length, it is at a given position. This is a lens upon focal length at a given position in front of ametropic eye, and it corrects the refractive error. Then we should have a different lens of focal length. A different lens of focal length is required when the correction is moved a distance d towards or away from the eye. So this d is the distance moved in meters. The value of d is positive if the lens is moved towards the eye, and negative if the lens is moved away from the eye. This Fn is the power of the lens and diopter at the new position, and Fo power of the lens at the original position, and d is the distance moved in meter. This formula is also used to convert glasses into contact lens. For example, in epic patient having 10 diopter lens, and we want to convert it into contact lens, and the original lens at a backward vertex distance of 15 millimeter. So by putting the values, the new contact lens power is 11.75 diopter. Example, suppose a high myope want to convert to contact lens, a high myope of minus 10 diopter. So by putting the values of minus 10 diopter and 14 millimeter, which is converted into meters, so he will need now 8.7 diopter contact lens. The position of the lens in front of the eye affects the optical correction, especially over 5 diopter lens. If it is more than 5 diopter, so then the position in front of the eye, it affects the optical correction of ametropia. This is especially true in aphakia, where high power lenses are prescribed. So high power should be placed in back cell of the trial frame and the back vertex distance. The back vertex distance is the distance between the back of the lens and the cornea. It must be given with the prescription. So especially true in ametropia where high power lenses are prescribed. For this reason, the refractionist must state how far in front of the eye the trial lens is situated so that the dispensing optician can adjust the lens power if a contact lens is to be used, or if spectacles are to be worn at a different distance because of a high, for example, because of a high bridge nose or a deep set eyes. Therefore, any high power lens should be placed in the back sill of the trial frame, and the distance between the back of the lens and the cornea is measured. This is called back vertex distance. Must be given with all prescription over 5 diopters. This measurement may be made with a ruler held parallel to the arm of the trial frame by a ruler. Other means include small ruler which is slipped through a stenopic slit placed in the back sill of the trial frame until it touches the closed eyelid. 2 mm must be added to the measurement to correct the thickness of the lid. Spectacle magnification. The optical correction of ametropia is associated with a change in the retinal image size. The ratio between the corrected and uncorrected image size is known as spectacle magnification. Spectacle magnification is equal to correct image size divided by uncorrected image size. Clinically, it is more useful to compare the corrected ametropic image size with the emmetropic image size. This ratio is known as relative spectacle magnification. Corrected ametropic image size while emmetropic image size. In axial ametropia, if the correcting lens is placed at the anterior focal point of the eye, the image size is the same as emmetropia. The RSM is therefore unity. However, in axial myopia, if the correcting lens is placed at the anterior focal point of the eye, the image size is the same as emmetropia. In axial myopia, if the correcting lens is worn near the eye, then the anterior focal point, then the image size is increased. The relative spectacle magnification is therefore greater than unity. Contact lenses in axial myopia thus have a magnifying effect. So in axial myopia, increase image size, and refractive myopia, decrease image size. Axial hyperopia, decrease image size. Refractive hyperopia, increase image size. So simply remember that contact lens in axial myopia have a magnifying effect, and all the other are the reverse of these. And refractive hyperopia, like for example spectacle correction in ametropia, so it produces a relative spectacle magnification of 1.36 when placed at the anterior focal point of the apexic eye, which is 23.2 mm in front of the principal plane. However, when the contact lens is used, then the relative spectacle magnification is reduced to 1.1. So correction of apexic, which is a type of refractive hypermetropia. So the relative spectacle magnification 1.33. It means 33% larger magnification when spectacles are used. 1.11, 10% larger when contact lenses are used. When intraocular implant is used, then no magnification. Spectacles are at 12 to 15 mm, but if spectacles are placed at the 23.2 mm, then it will be 36% magnification. Now, optical problems in correcting apakia with spectacles. All aphakic spectacles wearer have to contend with several problems due to the high refractive power of the lenses required, approximately plus 10 diopter or more. The use of a contact lens or an intraocular implant which reduces the relative spectacle magnification to 1.1 or 1.0 overcome these problems. So the first problem, the patient misjudges distance. RSM, relative spectacle magnification produced by aphakic spectacles correction is 1.33. So the image produced in the corrected aphakic eye is 1/3 larger than the image formed in an ametropic eye. So objects appear to be closer to the eye than they really are. So objects appear closer because of the increased visual angle subtended at the eye. The patient misjudges distance. There is false enhanced performance of standard test of visual acuity because of the produced magnification. So 6/9 visual acuity is equivalent to 6/12 of an emetropic eye. Also, the lenses used in aphakic spectacles are subject to the aberrations, which we have discussed in Chapter 8. In particular, image distortion is very troublesome to the newly aphakic patient. Straight lines appear curved except when viewed through a very small axial zone of the lens. This is known as pincushion effect. The linear environment thus appears as disconcerting curves, and these changes their shape as the patient moves his eyes and looks through different zones of his lenses. Patients usually adapt to this by learning to restrict their gaze to the axial zone of their lenses, and by moving their head rather than their eyes to look around. The prismatic effect in Chapter 5 of aphakic spectacle lenses produces ring scotoma all around the edge of the lens. This scotoma may well cause patient to trip over unseen obstructions in their path. Also, the direction of the ring scotoma changes as the patient moves his eyes, and objects may appear out of the scotoma or disappear into it. This is the jack-in-the-box phenomena. So, jack-in-the-box phenomena is the disappearance and re-emergence of an object. Because as the eye rotates, the ring scotoma moves in the opposite direction. So when a patient tries to look at the object, it disappears in the ring scotoma and then reappears in the peripheral vision when he looks away. Finally, high power glass lenses are heavy. They are heavy, may consequently cause the spectacles to slip down the patient's nose, thus altering the effective power of the lens. Heavy spectacles are also uncomfortable to wear. Weight may be reduced by the use of plastic lenses, but these tend to scratch, especially if laid face downward when not in use. Another means of reducing lens weight and thickness is by the use of lenticular form of lens. A lenticular lens has only a central portion of or aperture worked to prescription, the surrounding margin of the lens acting only as a carrier. However, the field of vision is necessarily reduced. The foregoing aberration and the prismatic effect and its consequences can all be eliminated by the use of contact lens or intraocular implants. Advantage of these two forms of correction stem from the fact that in each case the correcting lens becomes an integral part of the optical system of the eye. Correction of unilateral aphakia. Spectacle correction of unilateral apakia eye can achieve a clear retinal image, but within relative spectacle magnification of 33%, the image in the apachic eye is one-third larger than the image of the normal fellow eye. So the patient is unable to fuse images of such unequal size. This is known as anisoconia and complains of seeing double. The use of a contact lens or intraocular implant reduces the RSM to 1.1 or 1.0 respectively. The image in the apachic eye will thus be the same size. In case of intraocular implant, are only 1/10 larger in case of contact lens. In either event, the image can be fused and binocularity restored. It is possible to produce spectacle lens which has no focusing power but which alters retinal image size by increasing the visual angle subtended by an object at the eye. This is known as angular magnification. Such a lens is known as isoconic lens. The magnification depends on the curvature of the front surface of the lens and on its thickness. Thus, to produce pure magnification, the front curvature and the lens thickness are calculated and the back curvature adjusted to render the lens afocal. Alternatively, a refractive correction may be imposed on such lens. However, the maximum magnification which can be achieved in practice by an isoconic lens is only 5%, which is insufficient to be a practical benefit in the correction of unilateral apakia. Isoconic lenses have been used to treat other causes of anisoconia, for example, different retinal image size in the two eyes, but they have fallen into disuse for several reasons. They are expensive, requiring to be individually made on special machinery. Also, they are thick and heavy to wear. Correction of apakia with intraocular lens. The insertion of intraocular lens within the apachic eye overcomes the optical disadvantages of apachic spectacles and the handling and wearing difficulties encountered with contact lens. The IOL becomes part of the optical system of the eye, and because it is situated at or very close to the position of the crystalline lens, problems with relative spectacle magnification do not arise. Post-operatively, it is desirable to predict the power of the IOL, which will render the individual patient ametropic or in some cases produce a desired refractive error. So many theoretical formulas have been devised for predicting IOL power based on the calculation of the divergence power required in the plane of the IOL at a known position within the eye. IOL power formula are divided into regression formula, theoretical formula. Regression formula results based on clinical practice feedback. For example, SRK1, SRK2. Theoretical formula calculation based on schematic eye. Hofer, Q, Haggis, Holliday, and SRKT. In order to apply SRK formula, the corneal refractive power is measured using keratometer. The axial length is measured by scan ultrasonography. The original SRK1 formula states that P is equal to A minus B multiply axial length in millimeter minus C multiply average K reading in diopter minus D multiply desired refraction. P is the IOL power in diopter. A is constant which reflects the position of the particular model of IOL within the eye. P is multiplication of constant is equal to 2.5 for the axial length. C is the multiplication constant, 0.9 for average K reading. D is the multiplication constant of the desired refraction. If IOL power for emetrope is more than 14 diopter, then D is 1.25. If IOL power for emetrope is less than 14 diopter, then D is equal to 1.0. If the IOL power has been calculated for a posterior chamber lens and at surgery an anterior chamber lens has to be used, The required IOL power must be reduced by the difference in the A constants of the IOL. The equivalent anterior chamber IOL is usually 2 diopter weaker than a posterior chamber lens. Anterior chamber lens has a lower A constant. The original SRK formula was found to be inaccurate for eyes of short or long axial length, short less than 22 and long more than 24.5. So introduction of SRK2 formula, which incorporates the following correction. The A constant is adjusted and termed A1 in stepwise way over the range of axial length. For axial length less than 20, A1, the adjusted A constant is A plus 3. For axial length 20 mm to less than 21 mm, the adjusted A constant is A plus 2. Between 21 and 22, it is A plus 1. 22 to less than 24.5, it is A1 is equal to A. For higher, for more than 24.5, higher axial length, it is A minus 0.5. Further refinement, the theoretical SRK-T formula has been devised to improve the accuracy when very high or very low IOL powers are required. A-scan ultrasonography. To accurately predict IOL power, it is essential to measure the axial length along the visual axis of the eye, a straight line that passes through both the centers of the pupil and the center of the fovea. A probe emitting pulses of ultrasound is lightly applied to the cornea. The ultrasound passes through the eye and is reflected at the interface between the media of different acoustic density, i.e. from the posterior corneal surface, the anterior and posterior surface of the lens, and the retina and sclera. Since the speeds of ultrasound in the various ocular media are known, the axial length may be calculated. Ultrasound energy travels faster the more the denser the medium. A correction factor must be applied if the vitreous has been replaced by silicone oil. Since the speed of ultrasound in various ocular media are known, the axial length may be calculated. Ultrasound energy travels faster in the more denser medium, so a correction factor must be applied if the vitreous has been replaced by silicone oil. The highly myopic eye with a posterior stapyloma poses a particular problem, as the stapyloma may be beyond the range of measurement of some A-scan machine. In this situation, a B-scan, a two-dimensional ultrasound scan, will allow imaging of the shape of the eye, including the stapyloma, and the axial length can be measured from the image. A-scan ultrasound may also be used to measure corneal thickness. Special consideration: not all patients will be happy to be rendered emetropic or -1 diopter myopic. It is important to avoid significant anisometropia and all the problems that go with it, namely aniseikonia and disruption of binocular vision. Lifelong myopes do not like having to use convex reading glasses. So lifelong myopes do not like having to use convex reading glasses and prefer to use a concave distance correction. Multifocal IOLs. The following optical principles are implied in IOL design to achieve a multifocal effect. Concentric zones of graded power. The near zone is being at the center because of the pupil construct for near vision. This may cause difficulty for distance vision in bright light. Concentric annular zones, each of which has graded near to distance power, to provide near and distance correction over the whole lens aperture. Multiple ring tips worked on the posterior surface of a distance power IOL may be used to provide the second image for near vision by constructive interference between waves of light diffracted by various zones of the lens. Unlike multifocal spectacles, which have very different power at different zones of the lens, so that only one zone and power are used at a time, multifocal IOLs form multiple images over the whole lens aperture. In the case of bifocal IOLs, two images of an object are formed, one of which will fall on the retina when the object is at infinity, the other falling on the retina when the object is at the patient reading distance. Neither image is clear and bright as that formed by monofocal IOL. Furthermore, the second image forms a blur circle and the retina, which may degrade the perceived clarity of vision and cause glare when bright objects are viewed when driving at night. Refractive state after removal of the crystalline lens from a highly myopic eye. It should be recalled that the actual power of crystalline lens in isolation is plus 19 diopter, although it only contributes 15 diopter to overall refractive power of the eye. It might be supposed, therefore, that the axial myope of minus 15 diopter would be corrected by removing the crystalline lens. But because the degree of myopia is referred to by the strength of the spectacle correction, it is the axial myope of minus 18 to minus 20 diopter who become ametrope after cataract extraction. Standard intraocular implant lenses are usually approximately 19 diopter.